this evening's lesson, and I am your um, current host, HPU, and we are currently on week 7. I think in the previous lesson, I don't know whether it was chemistry, we had something we were supposed to finish. Yeah, it's chemistry. We were supposed to finish acidic, I think acidic stuff, something like that. Acidic. Oh no, we dealt with acidic redox reaction. So we're supposed to treat basic redox reaction. And I think for some reasons we were not able to complete that class. Really don't know how I used to make up for that one, but I must make up for that one. I must make up for that one. Maybe I would find a day during the week to put in the class, such as it will not just be for science students, but to be a day that our students are having lessons too. So, but for now, let's just resume with today's lesson. So we are treating chemical bonding. So we'll be treating the theories like the valence shell electron pair repulsion theory. We'll be seeing ionic and covalent bonding afresh. We'll be talking about stuffs like bond length, bond energy, polarity, and also hybridization. So during the course of this lesson, it might not already be that time consuming, depending on how the lesson is. But as usual, in case you have any question, just feel free to ask. Feel free to ask. And I know in the previous class, there was a point where I stated that, okay, we need to move fast for some reason, for time, because I did not want to be lagging topics or letting topics that are not, that we're supposed to treat for a particular day. I did not want to keep accumulating them for some other time. So, but as much as you can today, if you have any question or you're confused at any point during the lesson, just try to ask a question, feel free, and try to make it as just try to, if you're confused, don't hesitate, just communicate, just tell me. I'll try my best to see how much I can get back, simplify it, and so we can move forward as fast as possible. So moving in, we'll start by defining what chemical bonds are or chemical bonding is. So chemical bonding, from what I have here, refers to the force that holds atoms together in molecules and compounds. So as we know, everything that's probably will stick with another stuff, anything that is going to be bonded together, it has to be held by something. If you want to keep two things that are separate, you want to keep them together, you cannot just keep them side by side and they would stay, except they are resting on a base surface. But you cannot keep just any two entity like on the air together and they would stay the way they are. They would just fall, or somehow they would separate from themselves for some reasons, except they are being held together by a kind of force. So now we're seeing this particular phenomenon in terms of chemistry and seeing how bonds are being formed, also how bonding affects the structure of different molecules. So in this lesson, we will talk about how electron pairs affect structure of organism. But before I get to that portion, I would find a time where I would explain what I mean by electron pair. So for now, I just defined bonding, and I said it refers to the force that tries to hold atoms together in a molecule or in a compound. And also I said that I have here that atoms bond to achieve stable electronic configuration. So there is this idea that happens generally in life, that anything that is unstable always do anything possible to become stable. Anything that is unstable will try as much as it can to do something to become stable, so long as it has the energy. Even humans, if probably a human is probably in an uncomfortable position, he will try to adjust. Babies too, if they are not comfortable in the womb, they will try to readjust. Even in real life, if they are sleeping, even us as we are sleeping, if a particular position is uncomfortable for us, we will try to adjust to balance off. So that's the same thing that happens in terms of molecules or compounds. They try to adjust whenever they seem like as if there is things are not really balanced, or they are experiencing discomfort of any sort, they will try to adjust themselves the way that they will get comfort. So this explanation I'm giving now is going to be important because we'll read it later on in this lesson. So atoms bond to achieve stable electronic configuration. So everything that atoms try to do in order for them to exist as either a molecule or compound or even an atom, they do it for the purpose of stability, so they can be as stable as possible. So anything that can make them stable at any form that they find themselves, they will do that thing just to get stable. So before I move on to the next slide, I will need to explain what a bond is made up of. Every bond we see, every bond we say, okay, maybe chlorine is being bonded to sodium, barium is being bonded to chlorine, beryllium is being bonded to whatsoever element being bonded to another, even oxygen being bonded to oxygen. Every of those bonds, every single bond contains 2 electrons, every single bond. So if you're writing down, just write this probably at one point, key things to take note of. Every single bond is made up of 2 electrons. Every single, whether every bond, don't let me not say, let not be like I'm saying specifically single bonds, because in organic chemistry you hear stuff like single bond, double bond, triple bond. I'm not specifically trying to talk about just single bonds per se. I'm talking about every bond at all. Every bond, anything that is called a bond, for you to form one bond. I think that's the word, one bond. Every one bond is made up of 2 electrons. Every one bond is made up of 2 electrons. So that's one of the first things I would like you to take note of. I'd like you to take note of that. So they are made up of a pair. Every bond is made up of a pair of electrons, or made up of 2 electrons. So the next thing I would need you to write down is that atoms and molecules, and compounds, they try naturally to do everything possible to attain stability. Atoms, molecules, and compounds, they try everything possible in order to attain stability. They try to do anything possible to attain stability. So from our periodic table, I believe we should know that the group 18 elements, which some people know as the 8B elements, that's the noble gases, the ones at the end of the periodic table, at the right end of the periodic table, those final guys at the end, they are called noble gases or rare gases, and they include helium, neon, what's the other one? Neon, argon, and krypton, their likes. They are stable. They are stable. And each of these stable atoms, they are less reactive because of their stable. So they don't have, since they are stable already, they don't have any other thing, they would not worry. They would not want to worry themselves or to try to do anything that would take them out of their comfort zone. So they are already in their comfort zone. So for that reason, they are less reactive. What made me mention this, every single atom is trying to do everything to get to form a level of stability. And the most stable elements, or the most stable atoms, are those elements in the group 8B or group 18, depending on which name you choose to call them, group 18 or group 8B. So those guys, they have a stable electronic configuration. That is, their electron, their outermost shell is completely filled. That's one characteristic of the elements in the group 8B or the group 18 group, that is the group 18 or group 8B. They have complete electrons in their outermost shell. They have complete electrons in their outermost shell. So every atom or molecule every atom first would always try to want to be in that state of complete electronic configuration. So they will do anything, as I said, they will try to do anything possible to get to that state, even if it means for them to lose something or to gain something. So it's just the way I said it about humans. Anybody that is, I think I prefer using money most of the time to bring some of all these ideas to reality, because I think everybody can relate when it comes to money. Everybody that is broke, any broke person that is critically broke, like seriously broke, would, in their right senses, I'll say it that way, because some people might be comfortable. But every reasonable person that happens to find themselves as being broke would try as much as they can to leave that level of brokenness. Some of them might settle at level of just comfort. Some might want to get to levels of luxury. Some might want to go to levels of extravagance, but they would always want to leave the level of just that serious abject poverty. So the same thing with all these electrons. When they are uncomfortable, they see themselves as being disturbed, like completely disturbed. So they will try to do anything if it means for them to cut off their hand or to buy an extra hat. They would not mind doing all these things. So they try to do anything just to attain stability. So this is the second statement that I'm making. They will try to make and do anything to ensure stability. So for my second sentence, I said atoms bond to achieve stable electronic configuration. So this is one of the reasons why atoms bond, because when they form bond, when they bond with any other element to form a molecule, they are attaining stability because they will give off the electron that is discomforting to them, or they will gain an electron that they are lacking to attain stability. So when they try doing anything possible to gain stability. And one of the ways that they try attaining stability is by forming bonds. So they will form atoms will want to form bonds in order to get stability. So they could form bonds either ionically or covalently or whatsoever method based on the bonds pattern I taught in one of the previous classes. So they will do anything to just form to attain stability. Let's move on to the next slide. So we have what is called ionic bonds. So it involves complete transfer of electrons from one species to another, and usually from metals to non-metals. So when you hear about ionic bond or ionic compounds, your head should always spin off. First thing that it's involving a metal and a non-metal. When you hear ionic, your head should always go straight to metal and non-metal. Their union between metal and non-metals. It usually forms ionic bonds. Usually form ionic bonds. So when you have ionic bonds, what happens is the metals transfer their discomforting electron to the non-metals that actually need this electron to breathe well. Just like I say, metals, they are like guys that, or they are like people that they are feeling hot and they have sweater on them. So, and someone is by their side that is feeling really cold. So they will try as much as possible to remove that sweater from themselves completely and give it to the person so the person will wear, because the person is feeling cold while they are feeling hot. So they will give it to the person. And that kind of exchange, that transfer of material to the other person would cause a kind of friendship between both of them, or a kind of union. So that's actually how ionic bonds form. The metal would transfer its own electron that it finds discomforting. That electron is actually making the metal feel uncomfortable. So it will give up its electron to the one that actually needs the electron. And that way it forms a bond. So the metal might give one electron, might give two electrons, depending. But usually, every bond it forms by giving off an electron. These bonds, they are formed between metals and non-metals. In the case where the metal transfers the electron completely to the non-metal. And once it does this, it attains a kind of net positive charge. And when this net positive, because it has the net positive charge, it is called a cation. So ionic bond lists the formation of cations and anions. So cations are positively charged ions, while anions are negatively charged ions. I don't know, are you guys still with me?
Yes, sir.
Okay. So now, moving on, you can see from my example, I use one of the common examples for ionic bond, where it's a bond case between sodium and chlorine, where sodium has one electron in its outermost shell and is given to chlorine that needs one electron to complete its own outermost shell. So this electron, when it goes to chlorine pairs it up with one of its electrons to form that bond, because chlorine actually needs one of the electron. So it has one, needing one. So as it collects the one from sodium, it joins with its own and forms a new bond between sodium. So that is for ionic bonds. So the way ionic bonds form is this way we can see from this slide. I don't know, you can see my slide, right?
Yes, sir.
Okay, so for every ionic bond, there is always a give off of electron and also a gain of electron. And the give off is always done by the metal, and the gain is always done by the non-metal. So this is actually how the reaction, the single half reactions always happen. Like you'd have the atom giving off an electron to form a positive charge. Then on the other end, the non-metal will be the non-metal accepting an electron to give a negatively charged ion, that's an ion, an anion. So the metals always give off electron so that their products will now be their new state plus an electron. While the non-metals is their initial state plus an electron give their new states as ions. So this is actually how the electron equation is usually looking like for ionic bonds. So I have a quick question to ask now. I think this question should be a simple one. There's no need for me to hide it. The question is asking that which of these compounds are formed by ionic bonds. So it's just what we have at the back, sodium chloride. So if you look at this now, you will see this kind of stuff in your exam. You can see something like this, which of these are ionic bonds or stuff like that. So how you would tell is when you can be able to tell whether you have a metal and a non-metal. If you have anywhere you have a metal and non-metal, usually that point is going to be an ionic bond. Every time you see a metal and non-metal, if you should check crucially, you would see an ionic bond. So why I'm saying not generally every time is because there's some exceptions where that kind of thing will not hold true. But for basic level, you would always see it as when you see a metal bonded to a non-metal, you get an ionic bond. So moving on, we have covalent bond. So this is another kind of bond that forms. So this covalent bond, it actually forms
Sorry, sir.
when, yeah, I
Sorry,
can hear
sir.
you.
Sorry, sir. Can you take it back to the last slide where that question is? I'm trying to get it right. Thank you.
Okay, you're welcome.
Yeah, you can take
So
it down now.
okay, so if I should explain it before I move on, here with option A, we have hydrogen. Hydrogen is a gas and is a non-metal. Oxygen is a gas and is non-metal. So two non-metals cannot form an ionic bond. Here we have carbon and hydrogen. Hydrogen is a non-metal, carbon is a non-metal. So two non-metal cannot form an ionic bond. So this is not an ionic bond. So here we have sodium and chlorine. Sodium is a metal, chlorine is a non-metal. So this is most likely the answer. So here we have, to confirm, here we have what they call it, nitrogen, non-metal, hydrogen, non-metal. So because we have all these ones, non-metal, 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 aside this one having metal and non-metal, we can tell that this is actually the one that forms an ionic bond because it's a combination of metals and non-metals. So that's like, it's simple how to solve this kind of question. So let's go to covalent bonds. So for covalent bonding, it involves sharing of electron between non-metal, between two non-metals. And the shared electron is going to belong to both species. The shared electron is going to belong to both species. So how does this happen? Unlike ionic bond, where there is a complete electron transfer, just like as if um, for covalent bond, if I should use the cold person example now, it's like as if, okay, oh, I'm feeling cold. I have a big blanket. My friend beside me is also feeling cold. No, I'm feeling cold. I have a small blanket. Or no, not even that way. Let's use food for this example. I'm hungry. I have white rice. I don't have stew. Okay, I have
Excuse
gari. I
me.
don't have stew. Yeah, I can hear you.
Excuse me, sir.
Yeah, I can hear you.
Explaining
Go
for
on, I can hear you.
I can't see your
You
screen.
said
I explain You are explaining for value.
you're
The screen is okay now.
okay, you can see it now.
Yes, sir. Thank
Okay, you're welcome. So the example of what covalent bond looks like is we have two people. One of them has gari, does not have soup. The other one has soup, does not have gari. So both of them are seriously hungry. The other one cannot eat the gari alone because he will not even be able to pass his throat like that. The other one that has soup is really hungry. Just drinking soup will not satisfy him. So now he has to find someone that complements him, that has what he needs, and he has what the person needs. So that way now he carries his soup to the guy that has gari. The guy carries his gari and comes to the guy that has soup, and both of them would eat together, both of them will now eat and become full. So that's actually how covalent bonds happen. They share what they have amongst themselves, so that nobody will say the food is completely my own, or the other one will say the food is completely his own. So the food is our own because both of us brought a share. So that's what we have here. That's what I meant by saying the shared electron belongs to both atoms. The shared electron belongs to both atoms. So this is actually how this is actually how covalent bonding occurs. We have, and it usually happens mostly between two non-metals. It happens mostly between two non-metals. And examples of this kind of bonding is when we have hydrogen bonding to hydrogen to give hydrogen gas, chlorine bonding to another chlorine to give chlorine gas, carbon bonding to 4 different hydrogens to give what they call it, to give methane. So this kind of bonding, if it were to be in biology, we'll call it a symbiotic mutualism, where you have a relationship where both partners are benefiting from each other. So that's what covalent bonds look like. So that they form, these half covalent bonds are formed. They are formed between non-metals, where one of them receives the electron from the other one. The other one also gives his own electron, so that nobody can drag who is the owner. So let me move forward. So how do covalent bonds form? It forms from the share of electron, as I mentioned. Each atom contributes 1 or more electrons to form the shared pair. Each atom contributes 1 or more electrons to form the shared pair of electrons. So before they would form a bond, I said there would always be 2 electrons in each bond. So these guys now, to form any bond with themselves, they will be like contribute or contribute. So if anybody that contributes and the other person contributes, they will form a kind of union bond. That's actually how covalent bonds form by sharing. An example here, carbon and hydrogen in methane. What I have here is carbon and hydrogen in methane. This is methane, CH4. So now we are seeing 4 hydrogen and we are seeing 1 carbon. So what happens here is carbon has 4 electrons in its outermost shell on this state, because now it's a hybridized carbon. So this carbon now, it has, later on in this lesson, we'll see what I mean by hybridized carbon. So this carbon now, it has 4 electrons that it can share, 4 free single electrons that it can share. So 4 free single electrons that it can share. So these electrons that it has to share, hydrogen has 1 electron that it can share. So each of the hydrogen will come and meet carbon and say, please, let's share now. I have Gary. All the hydrogens, let's say they have Gary. Carbon has 4 plates of soup or 4 soups, 4 plates of soups. And carbon is the bigger guy. So one hydrogen, you say, I don't usually eat much, I beg. Let's see my Gary. Let's bond, let's share. Carbon will give him soup. Then both of them will eat together. As they are eating together, another person will say, I beg, if I have Gary extra, please, I want to eat with your soup. Your soup will still be able to reach me. Carbon will say, yeah, no, I'll come and join. Then another hydrogen will come in, do the same thing, another hydrogen will come in. So this is how it happens between carbon and hydrogen. So you have carbon sharing its 4 plates of soup with hydrogens having 4 wraps of Gary, each of them having one wrap. So they will donate their one wrap to eat the Gary. So that's actually the let's say the visual explanation of what happens in these kinds of bonds. So take note now. This is another thing I think you should take note of. When you have an atom, the atom would only be willing to give off an electron that is unpaired in its outermost shell. It's very important that you take note of this thing. Before an atom forms a bond, that bond must constitute its unpaired electron, must constitute part of its unpaired electron. So an electron that, what I mean by paired electron and unpaired electron is, it's just like as if you remember Horn's rule, they said when you are filling atoms in the in electronic configuration, you put them in singly first, then before you start bonding them one by one. So now, before an atom will be willing to give an electron out to another species, it needs to be that it does not have that electron, it does not have its cover up. It's just like let me use another example an example that will fit in this thing clearly. It's just like as if every atom that has an electron has a socket and a plug. A socket and a plug. Every electron that every atom would need would be a combination of a socket and a plug. So if the atom now has sockets, or sockets, maybe let me say he has like 3 sockets and 2 of those sockets are filled up. He has plugged something on those 2 sockets. He will not say, hey, this person needs plug. I'll disconnect the one that I already have that is complete. He will say the only one that is available to give out is the one that is not filled up. So that's actually what I mean by paired electron. If the electron is not paired with another electron, the atom is not going to give up that electron. It's only unpaired electron that it gives for bonding. So take note of this particular sentence very well. It is only bonding pair. It's only unpaired electrons that are available for bonding. Only unpaired electrons are available for bonding. So when the electrons that are on that atom, they are paired up, that atom would have no business giving anybody, because giving anybody anything will mean it should open itself up. It would remove the socket from its own place. And normally everybody wants to have their sockets filled up. So everybody having their sockets, just like as if it's customer, you have your shop can contain 4 customers. You have four shops and you can contain 4 customers. You would not say, let me give one of my shop out that is full. I don't know. I'm trying to look for a more vivid example, but the idea is just every atom, every electron wants to exist like in twos. They want to exist in pairs. Every electron that any atom can have wants to exist in pairs. So atoms will be only willing to give any of his electron that is not paired. It will be only willing to give any of his electron that is not paired. If the electron is paired up already, it cannot give that electron out. It would not want to give that electron out. That's the simple thing. It would not want to give the electron out. If the electron is paired, it will not want to give that particular electron out, except something special happens, which we'll find out later, the kind of special stuff that really happen. So when we have carbon now, if you can draw carbon using that normal shell diagram, you will see that in the innermost shell, carbon is 6. It has 6 electrons total. In its innermost shell, it will always fill 2 electrons. That shell has filled up. In its outermost shell, it will fill 4 electrons. 1, 2, 3, 4. But in some cases, when you are filling it according to electronic configuration, 1s2, 2p, all those kind of stuff, you will see that those electrons that is filling them, there is one that is actually paired. Maybe when we go into electronic configuration, clearly you will see what I mean by that. But for now, just take this note. The only electrons that are available for bonding are unpaired electrons. Any paired electron in an atom is not easily given up for bonding. Any paired electron is not easily given up for bonding. So let's move on to the next slide. So here we have another question which I was trying to ask. I said, which of these molecules contain only covalent bonds? I don't know if you guys can still hear me. Okay. So here we have another example. It said, which of these contains only covalent bonds? So let's see. Calcium. We said one of the key forms of covalent bond forming is between non-metals. So here we have calcium. Calcium is a metal already. It's already giving a disqualification to this one. But let's see. The next one is a non-metal. So we're having a metal bonding to a non-metal. First, the non-metal is already telling you that no, this cannot be a covalent bond, because it usually happens between 2 non-metals. So this is already telling you that this is not a covalent bond. Here we have hydrogen. Hydrogen is a non-metal. Oxygen is also a non-metal. This one might be a suspect for the answer. Here we have sodium. Sodium is a metal. Bromine is a non-metal. This is not what we are looking for. We have potassium. Potassium is a metal. This is a non-metal. This is a non-metal. So though we have 2 non-metals inside here, we might find a covalent bond inside here, but the entire structure is not made up of covalent bond. So this one is also out. So the only one that is made up of completely covalent bond is here, where we have just non-metals bonding with themselves, hydrogen and oxygen. So the answer to this question is B, because covalent bonds are made up only between metals and non-metals most of the times. So I think I should move to the next slide. So now we'll be having a comparison between ionic bonding and covalent bonding. So ionic bonding, as I said, it involves metal plus non-metal. metal plus non-metal. While for covalence, it has metal plus non-metal plus metal. Non-metal plus metal gives you your covalent bond, while metal plus non-metal gives you your ionic bond. So another thing about ionic bond is it involves electron transfer. Electron transfer. While covalence involves electron sharing. Electron transfer, electron sharing. Electron transfer, electron sharing. So for covalent, it's electron sharing, while for ionic, it is electron transfer. So the example I gave for this one was I used the example in the case where we have someone that is feeling cold, another person that is feeling hot. The person that is feeling hot would always want to give up his sweater to the person that is feeling cold because the person that is feeling cold needs the sweater. So that's the kind of thing that happens. He gives it completely. He does not wear this sweater on his body and share with the other one. He gives it to the other person completely because him is completely feeling hot, so he would not want to wear the sweater. So that's for ionic bond. So for this one now is I have Gary, you have soup, let's collabo, that kind of stuff. That's what happens in covalent bond. It involves electron sharing, while this one involves electron transfer. So another thing is they form crystals. It's just a unique characteristic of ionic bonded compound. They form crystals, while this one form molecules. They form crystals, and this one they form molecules. So another property is that they have high melting points. They have high melting points for ionic compounds, while for covalent compound, they have low melting points. They have low melting points. So let's move on to our next slide. So in this next slide, we'll be talking about bond energy and bond length. So first off, I remember from the beginning, I talked about chemical bond, and I said for anything to bond, there has to be a force combining the two things together. So now we are now trying to see how strong that force is. That's what we are trying to talk about when we're talking about bond energy. So bond energy is the amount of energy required to break a bond. It is the energy required to break a bond. So you can only tell that someone has a strong defense when it takes time or it takes enough energy to break that defense. So that is why they call bond energy the energy required to break a bond. So you cannot tell how strong a bond is until you've calculated it based on how much energy you spend trying to break that bond. So when you've tried, and it was very hard, you can tell the bond energy for this thing is very high. But if you just try small and you got it, you be like, the bond energy this species is low. So that's how the idea goes. The amount of energy required to break a bond is what is known as the bond energy. And the stronger bond energy, stronger bonds energy, stronger bonds have higher energy. Stronger bonds have higher energy. So now, when you now have bond length now is dependent on several factors, but we'll talk about it shortly. Bond length, it is the distance between the center of one atom that is bonding and the center of the other atom that is bonding. The center of one atom that is bonding and the center of another atom that is bonding. So now, let me see if I can use an example to explain this now. When you have two people that are just friends and they're trying to greet with a hug, there is how their hug will be. Their hug will be kind of not too, on a normal sense, supposed to be not too close. It's just be simple hug, like all this one-sided hug. There will be distance between them. Maybe even if they want to snap self, they will snap, they will not really come clinging themselves. They will have some kind of distance. So because of the relationship between them is not that strong. So, but when it's between two people that they have strong relationship, the distance between their body when they're trying to take that kind of picture will be very close. They will hold themselves as tight as possible because there is a relationship, a strong relationship between them. So that's the same thing that happens in bond length. When you have a strong bond or something that has a stronger bond, it tells that the bond length, that is the distance between the two atoms, their nucleus, their center, the distance between their centers will become shorter. So that's what I have in this sentence. Shorter bonds tell that you have stronger bonds. Sorry, shorter bonds supposed to be, shorter bond tells that you have stronger bonds. So when you try to snap a picture with, maybe you try to snap a picture with a friend, you and the friend is in that picture. Someone can tell how close you are based on how the distance between you and the person is on that picture, on a normal sense. So if the distance between you and someone is there is distance, why distance? It tells that okay, these people are not close, they don't have strong bond with themselves. So because of the longer distance, it can tell that they have weaker bonding between themselves. But now, if they are very close, they are clingy with themselves, the distance between them is very short. You can tell that they have strong bond between themselves. So that's what this idea is about. So shorter bonds will tell that there is a stronger bond, while longer bonds will tell that there is a weaker bond. Shorter bond tells that there is a stronger bond, while longer bond tell that there is a weaker bond. So we have here short, strong. The other side would have long, weak. So I hope that one is clear. So this is how these ideas or this stuff they play out. So let's move on to what's called bond polarity. So first, I think in one of our lessons, I talked about polarity, and I said polarity occurs when there is complete difference between, or there are two different species having contrasting characteristics. So that's how polarity occurs. So let me see what I have as a definition here. I said polarity arises when there is an unequal sharing of electrons due to difference in electronegativity. So this one, they're trying to explain why polarity occurs. So, but real sense, how polarity happens in a molecule that's where there is bonding. There will be polarity when one of the electron seems to be dominant over the other one in terms of attracting electron to himself. So in ionic bonds now, you see that one of them is holding the electron to himself. It attracted more electrons to itself. He collected the electron and stayed on his own. So in this kind of bonds now, you would say there is polarity. When one electron takes more, when one atom takes more of the electron, when one atom takes more of the electron that is involved in that bonding, or when it attracts more of the electron towards itself in that particular bonding setting, you will say it would give rise to what is called polarization. That is, that one that has taken more electron will become negative. It will become overall negative. While the one that is positive will become kind of overall positive. The one that lost electron will be kind of overall positive. So the one that accepted the electron will become happier. He has created many people's own electron. He will become happier. While the one that has lost most of his electrons will become sad. So now, because of the existence of sad and happy, so long as there is a trace of sadness and happiness existing together, there is polarity in that union. There is polarity in that union. So, but if both parties are happy, guys, maybe you did not experience any bad thing, I did not experience any bad thing, both of them are happy. There is no difference between our mood. There is no polarity. You cannot say that there is polarity between us because we have similar mood. So polarity occurs when there is a difference between the electron density in a bond. So that's the technical definition or the technical explanation of it. When a species, in real sense, when a species attracts more electrons to itself than the other electron involved in the bonding, they would form polarity. But when there is an equal sharing, a form of equal sharing of the electron, like what we can see in covalent bond, there is usually no polarity. I don't know if anybody has a question on what we've been teaching so far.
You said polarity, but when
Okay, polarity occurs when there is a difference in the overall positivity and negativity of two species involved in a bond. Polarity occurs when there is a difference in positivity and negativity on the two atoms involved in a bond. So just like as if we have yes, let me use this example, a tug of war. We have tug of war. Maybe in the team, there are two teams where everybody has equal strength. We have equal strength. The girls' strength are equal to the guys. Like the girls' strength, maybe the girls' strength is like 10 Newton. The guys' strength overall, all the guys, they have like 10 guys. They have 10 girls. But the summation of all the guys' strength is going to give 40. Summation of all the girls' strength is going to give you 20. So if there's a tug of war and they pack all the guys to one side, the guys would overcome the girls. And that kind of imbalance where the guys can easily pull the girl, they pull the girl more, they are stronger than the girls. That kind of imbalance in the strength is what gives rise to what is called polarity, where the guys pull the girls more to themselves. That's polarity. Or in the case where you split the number of girls, you say, okay, oh, the 10 guys that are on this side, you split them into two, put them 5 on the other side, the 10 girls on the other side, you split them, put 5 girls, 5 boys. At that kind of case, when you start the tug of war, the line would barely move. There will be no difference in the movement of the flag or the center mark. There will be no movement. You will not notice any. It's just like as if two people are holding the rope. Nothing is happening. Nobody is moving. Nobody is moving forward. Nobody is moving back. So that state of uniform strength or uniform kind of pattern or uniform existence is a kind of condition that you see that there is no polarity. When there is kind of balance in the electronegativity of two species involved in a bond, there is no polarity. But when there is an imbalance between the electronegativity of two species in a bond, you say there is polarity at that bond. I don't know whether it's clear or whether I'm passing the idea.
Yes, it's clear. It's clear.
Yeah,
We can
we
hear
can hear you,
you.
sir. We can hear you, sir.
Okay,
No
okay.
vex, sir.
So
It's
let's
Chelsea.
move.
Chelsea, guys.
You said? You said something. I think I did not really pick what you said. Okay.
Yes, sir. I was
Assume
one.
probably
I
it
was one
was.
that thought. I was saying that you should not be angry. That it's Chelsea that's causing all these things.
It's fine. It's fine. So, like that match that is possibly happening there, where it's happening, if Chelsea is stronger than the other people, there's going to be polarity. Goals will be more on one side, while the other people will lack goals. So that kind of incident where there is imbalance, where there is no draw, is kind of where there is real win on the game. You say that there is polarity. But when the two teams are equal, that there's draw, there is no polarity. So polarity occurs when one team is stronger than the other team, or when one end is stronger than the other end, or when there's difference in their aggregate score, their total score. So let's move on to our next slide. We have what is called dipole moment. Dipole moment. So dipole moment is a measure of a bond's polarity. So I was talking about polarity, and I was talking about that it is involved when it is usually, they talk about polarity when you come to a bond. You say, okay, is this bond polar or is not polar? So the bond is polar when there is the strength of the both atoms that are involved in that bond is different. When the electronegativity is different, you say the bond is polar. But when the electronegativity is the same, you say the bond is non-polar. So what is called, when we now talk about dipole moment, is trying to measure the level of polarity on each of the bond. Dipole moment is a measure of polarity on the bonds. So it's usually gotten by measuring the charge times the distance between the charges. The charge times distance between the charges. So that's the formula to calculate dipole moment. You barely see questions on dipole moment like that, but the idea is just to know what dipole moment is. It is the measure of the bond's polarity. I think most of the times you barely see questions that would come out to calculate the dipole moment, especially in chemistry. So mostly what you will see is probably theoretical questions in on it rather. So it indicates molecular polarity. The same thing we always said at the beginning. When you see that the dipole moment is increasing, it means that the molecule or the bond is more polar. There is difference in the electronegativity of the two species involved in that bond. So let's move on to the next portion of this lesson, talking about hybridization. Hybridization. So when we hear the word hybridization, this is a concept that's actually known majorly or basically it's talked about more in organic chemistry. It's talked about more in organic chemistry. So the idea of hybridization is kind of an interesting one. So how it happens is we would have orbitals mixing with themselves. And as a mix, they don't form, they don't remain the same. Yes, that's the word. When we have two orbitals mixing with themselves to give a new orbital, the new orbital will not be the same as the initial orbital. So how does this hybridization occur? I would start by definition. The definition of what hybridization is. Hybridization is the mixing of atomic orbitals to form new orbitals of equal energy. It is the mixing of atomic orbitals to form new orbitals of equal energy. So pay attention to some of these key parameters that are mentioned in this definition. It is the mixing of what? Atomic orbitals to do what? Form new orbitals. Then what? That the resulting new orbital would have an equal energy. So these are the four keynotes when you're trying to talk about hybridization. So if you're asked to define hybridization, mentioning these four things would show that you have a clear understanding of what the concept is about. So first off, it is involving the mixing of two different orbitals, not necessarily different, two orbitals, mixing of two orbitals. But usually it's always between two orbitals, different orbitals. It's mixing of two orbitals to form a new orbital that has equal energy. So how it happens is this: you would have probably usually the typical example, we'll be going to it now. Let's even go to it now. So we have three basic types of early level hybridization. There are many types of hybridization, but I think for this course scope, we'll be focusing on just the basic ones that you will see most of the times. You will see SP hybridization, you see SP2 hybridization, you see SP3 hybridization. In some other advanced level, you see SP3, SPD3, or you see D2, SP3. You see different types of other hybrid mixing. But now, what is all these things meaning? What is SP meaning? What is SP2 meaning? What is SP3 meaning? So now, in the common sense, we use carbon most of the time when we talk about hybridization. We have the electronic configuration of carbon being carbon has six electrons. So if you are writing the electronic configuration of carbon, you'll be having 1s2, 2s2, 2p4. That is the hybridization of carbon. So now, no, not 2p4, 2p2. Sorry, I made a mistake. 1s2, 2s2, 2p2. That's the normal carbon on the normal level. So what happens is now in that normal carbon, we have one orbital on the level 2, on the energy level of 2. We have one s orbital in the energy level of 2, and we have two orbitals in the energy level of what they call it, in the energy sorry, we have 3p orbitals in the energy level of 2. We have one s orbital in the energy level of 2. I don't know if I'm communicating. For that level, for the level 2, when you're writing orbitals, when you're writing electronic configuration, you would always have, under 2, you would have S and P. When you're writing 1s, 2s, 2p, you would always have 2. When you have 2, you cannot have 2d. You can never see an electronic configuration where you see 2d. So we're talking about an energy level, the number behind. Energy level of 2, you would always have S and P. It cannot be less than that. It's always S and P. It cannot be more than that. Sorry. So for this S and P now, for every of this energy level of 2, there is always one S orbital and 3p orbitals. Every energy level of 2, there's always one s orbital and 3p orbitals. One s orbital and 3p orbital. One s orbital and 3p orbital. So now what then happens is this: hybridization occurs when that one s mixes up with different number of these p orbitals. When it mixes up with different number of these p orbitals. So in a case where we have this 1s mixing up with just a single p orbital, it is called an sp hybridization. An sp hybridization. So just like as if we are saying, let me use a funny adult sentence that would make us, I will bring it to our head. We have probably a womanizing one promiscuous person that is dating, like if it's a man, we have one man in the midst of 3 girls, or if it's a girl, one girl in the midst of 3 guys. So let me just pick one gender. Let me say gender A and gender B. Yes, so I will not be selecting anyone. So we have gender A in the midst of gender B. So we have 3B, 3 of that gender B, and 1 of that gender A. So this 1 of that gender A can deceive these people in different ways. This gender A can date only 1 of the B. When it's dating only 1 of the B, it forms what is called like an SP hybrid orbital. That it has only 1 boy or girlfriend. So now, when this gender A now is mixing with, is having more than 1 boy or girl, 1 girlfriend or boyfriend, that is now mingling with 2 people in that classroom. We have a classroom of 4 people. 1 of them is a guy. Let me just use a guy. 1 of them is a guy, and 3 are girls. Then 1 guy is dating 1 girl. It's a good thing. It's not bad. 1 guy is dating 1 girl. You'd have an SP relationship or an SP hybridization kind of setting. So when you have that 1 guy now dating 2 other girls in that same class, you have what is called your SP2 hybridization. You have your SP2 hybridization. That is 1 S orbital mixing with 2 P orbital. He's dating this of them without any of them knowing. He's dating both of them. So now, when you have the SP3 is when the same 1 guy is dating all 3 girls in the class, he's dating all of them at the same time. So this is the SP3 hybridization. So what is happening now is this. When he's dating just 1 person, people will see him as this is his girlfriend. And other girls, they will see them as being single. You get? They'll say this one is this guy and this girl, they are in a relationship. So they'll see both of them as in a relationship. They see the girl, they'll say the girl is in a relationship. They see the guy, they'll say the guy is in a relationship. So, but now, when the guy is dating, let's go back to SP2. When the guy is dating 2 girls, people that know the girl will say the girl is in a relationship. One of the girls will say one of the girls is in a relationship. People that know the next girl will say she's in a relationship. People that know the guy will say the guy is in a relationship. But now, he's dating, there are 3 people that are in relationships in that class. Though they are playing themselves, but there are 3 people that are in relationships. So now, these 3 people, they are categorized as people being in the same level relationship. They are in the same level. That is energy. They have the same status. Being in a relationship, that's their status. They are in a relationship. So now, when we now have the 1 guy mixing with 3 girls in the class, you will say that everybody in that class have the same status. They have in a relationship, in a relationship, in a relationship. You get? So that is how hybridization works. You would have when 1 orbital mixes with another orbital to form a new, or to update his status to become equal. Both of them will now update their status. Okay, I'm in a relationship, he's in a relationship also. So they've updated their status now. They have identical status. So in sense of this strength or high bonding, they will call it, they have a new energy. They form a new orbital. So when he merges with 2 other people, you now have all of them saying, everything their status saying in a relationship, in a relationship, in a relationship. So all of them status will be in a relationship. It's only 1 person that is not in a relationship. So these 3 mixed up orbitals, they would have the same status. They would have the same status. So now when you now have the same guy mingling with all 3 of them, they would have the 3 of them being in the same status, in a relationship, in a relationship. So anyhow, so long as they mix, they would have to update their status to being in a relationship, so long as they've mixed. So they would have the people that are in that relationship that are involved, their status will be updated to in a relationship. So that's actually how hybridization occurs. I don't know if anybody has a question about this stuff that's happening that I've explained so far. If anything is still confusing to you, just mention it to me. Hello, can you guys still hear me?
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay, so that's actually how I believe you guys are following, though, because nobody is asking me a question. So that is how hybridization occurs. You would have an orbital mixing with another orbital. So the one that it mixes with, both of them would have the same new status or the same new strength. So when it mixes with more, all 3 would have the same new strength. When it mixes with extra, all of them that are involved would have the same new strength. So that's what happens when you see SP1, SP or SP, SP2, SP3. SP means 1 s orbital mixing with 1 p orbital to form a new orbital, or to to update to form a new updated status for these two orbitals that were involved. They will then be called in a relationship that's SP. We'll call them SP. This one is SP, this one is SP, this one is SP. So just like as if it's criminal, the same thing with criminals. Someone that's found to they carried out an operation, an investigation, they found out that okay, these people were criminals. So then we are involved. All the people involved, they'll call them criminals. So if they found another person extra, that person would have the same tag. A new criminal is a culprit among them. So if another person, they find another person, they will still tag all of them to be in the same level. So all of them will be on the same energy level. So that's the same idea that happens in hybridization. So examples of species that have this kind of hybridization. We have for the first one, we have beryllium chloride or barium dichloride. It's an example of species that you can see the sp hybridization, and it happens also in alkynes. So the structure of these kind of compounds are usually linear shaped. We'll go to structures later on and you will see how this thing applies. So the structures of these compounds are usually linear shaped. So when you have an sp2 hybridization, you would have the shape is usually going to be a trigonal planar shape. A trigonal planar shape. This one is a constant. So if you're writing, you could write down as things that you should just memorize. It's not changing anyhow. It's just something that is constant. When you have an sp2, usually the structure would always be a trigonal planar shape. So an example of that kind of elements or molecules that exist such as boron trifluoride. So another one now is sp3. Usually their shape is usually tetrahedral. Anytime you see something that has an sp3 hybridization, if it has an sp3 hybridization, you can tell the structure already that it's going to have a tetrahedral shape or a tetrahedral structure. So, and example, we have methane or other alkanes. So let's move on to, I think, one of the last portions of today's lesson, and it's called the Vesper's theory or VSEPR theory. I know they pronounce it as Vesper, but in real pronunciation, in real sense, it's not really Vesper, it is VSEPR theory. So this theory is actually a theory that tries to talk about the structure of elements or the shapes of molecules, not elements, the shapes of molecules as a result of the presence of an electron pair. So the meaning of this VSEPR is valence shell electron pair repulsion. Valence shell electron pair repulsion. I think this was one of the interesting topics I had during my undergraduate days. It's one of the very interesting topics. So it is called valence shell electron pair repulsion theory. And the theory tries to predict the molecular shape of species. It tries to predict their shape. So we'll see how these things can predict. So remember at one point during the lesson, I said there's something that they call bonding pair. And at one point, I think on my second slide, I mentioned, or my third slide, I mentioned something about bonding pair and lone pair or non-bonding pair. I said the ones that are available for bonding are the ones that are unpaired. The ones that are not available for bonding are the ones that are paired electrons. So paired electrons are always called lone pair. Paired electrons in an atom, they are always called lone pairs. So if you're writing, you can write, in case, because I might be using both words or both sentence, or is it what sentence are called? Both words or both namings for each of them. So unpaired electrons are usually called, no, not unpaired, sorry, paired electrons. Paired electrons are usually called in full lone pairs or lone pairs of electron. Lone pairs of electron. So while unpaired electrons are usually called, and those lone pairs of electrons, they are also called non-bonding pairs. So they have three names. Unpaired electron. Sorry, they have three names: paired electron, or lone pair, or non-bonding pair. Paired electrons, or lone pair, or non-bonding pair. Paired electrons, or lone pair, or non-bonding pair. So these are the names of the non-bonding electrons. And due to the fact that they are non-bonding, they have something that they do to the shape of molecules. Due to the fact that they are present in any molecule, there is something that they do to the shape of that molecule. They alter its from the normal pattern that it's supposed to have been. So I'm trying to call back again our mind that at the beginning of this lesson, I was saying that electrons or atoms or even molecules will want to do anything possible to become in a stable state. They will try to do anything possible to become in a stable state. So when we come to this valence shell electron pair repulsion, valence shell electron pair repulsion, valence shell electron pair repulsion. So the word valence means the outermost shell. Valence shell, that is the outermost shell. Electron pair, the lone pairs or the non-bonding pairs or the paired electron. So that's the electron pair they're talking about. So the lone pair electron in the valence shell, that's what we are looking at. So this theory is about the lone pair of electron in the valence shell, that's in the outermost shell. So there is a kind of repulsion that they exhibit to other pairs that are formed, or to other pairs, that is other bonds that form later on. Them, they normally own the house, they stay on the elements. The non-bonding pair, that's the lone pair of electron, they have, like, let me just use an example. We have probably, let's say, an adopted child in a bad family. All this is our Cinderella story kind of stuff. We have two children of two, or let me say, a woman that has like 4 children. Then out of the 4 children, we have 3 of these children. They belong to her current husband. They are the main children of the current husband. Then one of the child is a child from another man. So there is the way that these children that are belonging to the main man will treat this child that is not belonging to the main child. In most cases, it usually happens that way, that they will treat that child differently. They will want to torment that child. They will want to push the child to the corner. So that's actually what happens in this PSEPR theory. That's what this theory is trying to talk about. How these lone pairs, they try to push away these other electrons or other electron pairs or other electrons present in that particular molecule that are not present, are not part of them. Just the analogy, I think the analogy of a family that is involving maybe even 7 children or 8 children, where let me say 4 children. A family that has 4 children, where 2 of the children are the children of the main man, and the other 2 children, they don't really belong to the new family. That is the main man in the foreign family. These 2 children that are the main children, they will treat these other children differently. So that treatment is what this theory is trying to talk about. That this treatment would alter the overall family view, how people will see the family. They will see the family as a family that has a different, people will have a different view of the family. It will not look like a normal family. It look like a kind of a family that has a level of dysfunctionality, depending on how they adjust themselves. So let's go on to what it's talking about mainly. So now, from this theory, it says that when you have a lone pair of electron on the valence shell of an atom, this lone pair would cause any other electron that is present to move as far as possible away from itself. It will push them as far away from itself as possible. It will distance them as far away from itself as possible. It will take the major balance. Then those other ones will now try to find a way to squeeze themselves anywhere possible. So that's what this lone pair of electron does. It pushes other people away, takes the major portion of the whole space. Then those other ones will have to manage anything that is remaining, trying to make themselves comfortable. It will first try to get comfortable, taking the major space. The other ones will now try to find comfort by anything present. So let's see how this thing happens. So in this diagram now, we have on this side, we are seeing on this side, this is the number of atoms that are involved. It's the number of atoms that are involved. Lone pair, I think I made a mistake here. So this number I was seeing here, 2, 3, 4, is representing the number of, here we have 5, 6. So this is 5 and 6, 5 and 6 here. We're talking about the number of lone pair of electrons. So in a molecule where we have 2 lone pair of electrons, these 2 lone pair of electrons will stay as wide apart from themselves as possible. So because of all electron pairs would always want to repel themselves. So if there are only two, they would stay extreme as but they would stay probably at the north and south pole. They will stretch yourself to the end extreme, stretch yourself to the extreme. So every other species cannot stay at that extreme for them. They will be the one that would occupy those extremes. They will take, like as if we are trying to talk about maybe hostel now. You come to an hostel, maybe all these kind of hostels that are crowded. The people that came in first, they will take the most comfortable areas and leave other people to manage any area that they see. They'll take the most comfortable bed, leave other people to manage the one that they see. So that's actually what lone pair of electrons they do. So when they come into these electrons, when they are in this atom, they will take the most convenient spots. They will first become stable first. They will adjust themselves so that they will get as comfortable as possible by spreading themselves as wide apart as possible. Then every other space around, other electrons will then find a way to fit in. So usually this is what happens when you have two lone pairs. They will stay at one side and the other one will stay at the second side. So when you have two lone pairs, one will stay at one end, the other one will stay at the other end, like as if they're staying north and south pole or east and west, as far as possible away. So when you have three, they will stay in a Y shape. The lone pair of electrons, they would occupy the Y shape. They would occupy the Y shape, as you can see here. They would occupy the Y shape. These dots that are seen here, the lone pair of electrons, they will occupy the Y shape. Why when they are three, they would occupy a shape that is looking like this. They would occupy a shape that is looking like that. I don't know how I want you to describe it because this is not a 3D view stuff, but I don't know if some people can get it. The person that is at top will stay as far away as he can. The person at this side will take as far away as he can. All of them will stay as far away as possible first. Then any other electron that is present would now manage any space that is remaining within them. So this is now what happens. This is how it happens to the shape of the electrons, the shape of electrons. So when you have two lone pairs of electrons, it usually causes the overall shape of the molecule to be linear. As you can see here, at this point here, we have linear. So two electrons, it makes them have linear shape. So when you have the same thing here, it gives you trigonal planar. The same thing with here. So here is when we have just one lone pair of electrons. Like this one, this line here, this middle line here, it's talking about when we have no lone pair at all, but we have the same number of atoms, the same number of bonds. So this first one is talking about lone pair of electrons, and that is making up the bond. I don't know if I'm communicating. I don't know if I'm communicating at all. The first portion is talking about two lone pair presence. The second portion is talking about a case where you're not talking where there is no lone pair at all. This is how the other people that come in would stay. So the first one is showing you how lone pairs will stay when they come in first. The second one is showing you how other people will stay when they come in first. Then now, this third one now is showing you how it will happen when you have a lone pair in between other people. The lone pair will take one of the dominant position, and other people will manage anything that is remaining. So now, if you can look at this now, in this first one now, we have two of them. They don't have anybody that is different from them. So they will stay as wide as possible. They will spread themselves throughout the room. So now, this one now, so the same thing. They don't have any lone pair. They will spread themselves the same way that all these lone pairs will spread themselves. So this one shape look like this one shape. This one shape will look like this one shape. This one shape, there is no lone pair. It will look exactly like the same way this one shape is. So now, but when you now have lone pairs, when you then have lone pairs, in this case now, when you have one lone pair replacing one of these electrons, that lone pair will take one of the major positions. Other ones will now have to stay. Because lone pair is not really a bond, it does not really form a bond, it's just an entity that is there. It just stays there. The real bonds that are formed now is this one and this one. This one and this one, they are the real bonds that are formed. So the lone pair is just an entity that is like a hunchback on the main atom, the main center atom. So regardless of the fact that it does not form a bond, the fact that it is present, it would behave like as though it is taking a position of a whole bond. Take a position of a whole bond. So the same thing that is happening here. This is how a normal bond will stay. But now this lone pair, now there's only two bonds here, 1 and 2 here. But now this lone pair took the position as though a whole bond. Normally, these other ones that are normal bond, they're supposed to stretch out because when they are two, they're supposed to just be like this. When they are two, when there are two this thing. Oh God, I don't know if I'm passing the message right. I don't know if I'm passing the message to you guys. I don't know. Are you guys following me?
Yes, sir. Yes, sir.
Uh,
Yes, sir.
Okay.
uh,
So when they are normal, when they are just two and we have a center atom, they're supposed to stay and look like this here. Because we have this one, and the center atom. It's supposed to be straight. But now this lone pair will cause it to bend. Because this lone pair is not really a bond. This is the bond. These are the bonds that are present. This one and this one. They're supposed to look like this on a normal, but because of the presence of the lone pair, they don't look like how they're supposed to look like. They're supposed to look like this, I mean. But because of the presence of the lone pair now, they have to bend themselves because of the lone pair will force them to stay in a different position, making them be like as if they have three people there. So now let's look at this one too now. In this case now, when it's just lone pair, this is how the structure would align. When it's just bonding pair, this is how the structure will align. But when we now have one lone pair, these are 1, 2, 3 bonded to the center. It's supposed to relax as this one up here would relax. It's supposed to relax as this one up here would relax. It's supposed to take a trigonal planar shape. But now, instead of it to take this trigonal planar shape, because of this lone pair, to make it behave like this one, this lone pair will take a space that's supposed to be there. It will take this space up and tell this one to go and fill in the boys' quarter. So now, when there are now two lone pairs now, these two lone pairs will take the same shape that other one, just they will take the major space. This one that has just two bonding pairs, supposed to behave like this linear at the top, because we have 1, 2 bonded to the center. Here we have 1, 2 bonded to the center at this top here, 1, 2 bonded to the center. So normally they're supposed to have this same shape, but because of this presence of these two lone pairs, they have to bend themselves even more than the way it was at this place. So they will bend themselves like the same way they bend here. So in this case too, this is how a scenario where we have 5 atoms or 5 bonding pair looks like. When we have 5 bonding pair, these are the structure will be like. When we have 5 lone pairs, these are it. When we have 5 lone pairs, these are it look like. When we have 5 bonding pairs, these are it look like. So, but when we start having one lone pair entering, it will force it from looking like how it's supposed to be. It will take a position that's supposed to be for another atom. Although it is not an entity that's supposed to stay on that place, but it just occupy that place. It's just like as if someone will see them and say, why are people staying like this? They know that there was actually a bully that stayed there that is very small and nobody is seeing. That just discomforted them and made them stay in this shape that they don't supposed to stay on normal. Normally, they're supposed to take this shape. Normally, because there are 4 being bonded to the center, they're supposed to take the shape of this one here. So I don't know if you guys are following me, but that's just the idea. The bonding pairs always try to fit into whatever space is left after the lone pair has taken its own space. So that's the idea. And the shapes of these things are now, when you have one bonding pair, these are their names below. One lone pair on a 3 atom molecule would cause angular shape. One lone pair on a 4 atom molecule would cause a trigonal shape. Two lone pair on a 3, that is one lone pair on a 3 atom molecule would give you angular. One lone pair on a 2 lone pair on a 2, that's this one supposed to look like this one, supposed to look like this one. But now the lone pairs is just changing their structure. So one lone pair in this one made this one angular. Another lone pair in this one made this one still look angular. Like 2 lone pair made them angular. This one even have a smaller angle compared to this one. So they shrink even more. So this one now supposed to look like this one. Supposed to look like this one. But now the lone pair is forcing it to change its position, because here we have 4 atoms present in this whole structure, 3 bonded to the center. Here we also have 4 atoms present, 3 bonded to the center one. Supposed to look alike. It's supposed to look alike. But due to the presence of the lone pair on top of this one, it's changed the structure. So that's actually how this lone pair happens. So the main idea is just understand how these things happen. The idea of what the lone pair of electron does, it causes them to repel from their normal position that is supposed to occupy. So that's the idea on lone pair electron, lone valence shell electron pair theory. So I think that should be all for this night class. That should be all for this night, and that's all we have on this slide for this night class. I don't know if anyone has a question.
Our question is based on past questions. I saw some past questions on this topic. So
Okay.
I want to ask if I can drop the past questions on the main group.
Which of the main group, the JUPEB group or this one, or the Central Store
The
private group?
central tutor, yes, sir. The central tutor private group, sir.
Yeah, you can drop it there. You can drop it there.
Okay, sir. Okay, sir. Thank you, sir.
No problem. You're welcome. So this the examples now, how you see this kind of questions in exam for the Valencia relation period, will give you a molecule, and you will need to know how the molecule looks like. So now this molecule now, it has 4 atoms total, where we have 3 hydrogen bonded to a center nitrogen. So now 3 hydrogen, normally the shape supposed to be when we have 4 atoms, it's supposed to have a pyramidal shape, a tetrahedral shape, this kind of stuff here. When we have, okay, this is not 4, this is 4, sorry, this is 4 molecules, 4 atoms. It's supposed to have a trigonal shape when we have 4 atoms totally. This is how it's supposed to look like. But now, because we have nitrogen has a lone pair of electrons. Nitrogen has a lone pair of electrons. That lone pair of electrons will cause the shape of this nitrogen atom to shift. So now the shape of this nitrogen now, suppose, if assuming you don't know that nitrogen has a lone pair of electrons, you would have predicted the shape to be trigonal planar. You'd have predicted the shape to be trigonal planar. But now, because of the presence of lone pair of electrons that nitrogen have, it will now have trigonal pyramidal instead of trigonal planar. So that's how this thing happens. So the correct answer here is not trigonal planar, it's trigonal pyramidal, because trigonal planar is if would have been the structure if there was no lone pair in this atom. But because there's a lone pair and the number of lone pair is 1, the structure will now have the structure of this kind of one that has that arrangement. 4 atoms, 1 lone pair. So this is 4 atoms, 1 lone pair. This is 3 atoms, 1 lone pair. 3 atoms, 2 lone pair. 4 atoms, no lone pair. 3 atoms, no lone pair. 5 atoms, no lone pair. So this is just how the arrangement is. So I think this one will be practice questions for you guys. You need to know, I believe by now everybody should be able to find what ionic bonds or ionic bonding is, and also what covalent bonding is, and you can also give examples. And you should be able to compare between, you should be able to explain the difference between SP, SP2, and SP3 hybridization. Because that's what this question is about. They say you should compare both of them. So what you are trying to do is to try to tell how both of them differ from each other and what makes up both of them. So then predicting the shape is to be able to look at the structure of this atom now, knowing what is how the thing bond. We have O at the center, bonded to hydrogen, bonded to another hydrogen. So why is it bent? They say water has a bent structure. The reason why is because of oxygen has 2 lone pairs of electrons. So when you have 3 atoms bonded together, but the center atom has 2 lone pair of electrons, the shape will look like this. 3 atoms, this is how it look like. No, this like this, look like this here. Because we have 3 atoms with 2 lone pair. So the shape will look like this, angular. 3 atoms with 2 lone pair. So how does it happen? We have oxygen. Oxygen is on its own center. It has 2 lone pair of electrons. Then it bonds with 2 hydrogen. So those 2 lone pair of electrons are the one that will cause the hydrogen. Instead of it to take a straight shape, oxygen at the center, this one at the other end, this one at the other end. Because of the lone pair will cause them to bend. When it causes them to bend, they will then have an angular shape. So the answer for this one, the predicting the shape, if you are predicting the shape is going to be angular. So I think maybe I gave an example. I gave what they call it in the last class. I gave an assignment in the last class. I don't think anybody has been submitting the assignments. So it's all good. It's all good. If you have any question, ask me, because I think we've come to the end of this class. So in summary, we talked about ionic bonds, and we know that ionic bond is a bond that is formed as a result of electron transfer, while covalence is formed by electron sharing. We talked about bond energy, bond length, and polarity. We also talked about hybridization and how hybridization is responsible for some shapes of molecule also. Then we also talked about the ESEPR theory. So if there is no question, I don't know. So if nobody is submitting an assignment, I will not be able to know where I need to focus more on or where I need to correct people on. So that's the purpose though. So with all those with everything that has gone on, I think we've come to the end of today's lesson. And wow. So we've come to the end of today's lesson. I'll be saying good night to everyone.